Hello, everyone. Welcome back to the last section of today's talks and lectures about quantum science, quantum technology, developing, well, in the grand thing that we call Latin America, Brazil, Spanish-speaking countries, Portuguese, French. It's really lovely to see the diversity of our subcontinent, as well as together with Spain and many other countries that we basically build the cultures that we live in, and then seeing that we can make great things in quantum and other technologies. So an example of that is the work that is going to be presented by Dennis Lima from the Federal University of Rio Grande do Norte in Brazil. The title of his talk is on the matrix representation of four discrete metric walk across η-Pseudo-Unitary groups and its application in Braid circuits. Welcome, Dennis. Thank you very much for joining us. Go ahead.
Thank you. So let's start. First, I introduce what we're going to talk about in this presentation, and I'm going to introduce the T-matrix theory and the S-matrix theory. Define the group, the maps, a S-matrix as scattering matrix to a transfer matrix. And when I do this, I'm walking a metric of a unitary group to another pseudo-unitary group. This metric I call eta, and I define another group, the group where this eta object, this eta metric walks. Then by invoking the diagrammatic interpretation, the physical interpretation of the scattering process, I introduce the A matrix. A matrix is a matrix that should grow the scattering diagram in a direction perpendicular to the direction of the T matrix. This is in a time model. And subsequently, I discuss the applications and limitations of this group, this technique to map two pseudo-unitary groups, and how we could use this to build large braid circuits, sort of emulating renormalization. But there are some infinities on the way. So first of all, the preliminaries. We need the unimodular unitary operators to build quantum circuits, and by stacking them here on these strings are mapping the input states to the output states in financial measurement. We build our quantum circuits. In case of a topological quantum circuit, we want operators that change topological properties of our states. So we're interested in using braid group and braid generators like this one, but in real life, as we manipulating several states and states that like anyons, like Professor Julia said, states that some of them are many body states, a phenomenon that occur due to many body interactions. In real life, we have things like this. A random link, a random knot. So we can apply these operators and try to extract topological properties through conductance. In this case, one-hour conductance that is related to the transfer matrix. This is to say, it's related to the scattering properties of our systems. So when we talk about S matrix and T matrix, we need to think of pseudo-unitary groups, because S matrix is a unitary operator. It's the limit of an evolution operator, a time evolution operator, when the the whole universe. But if you change the metric of if we prepare our system in another metric or analyze it in another metric, we can perform cloning of non-orthogonal states. And so, but this is going to be only motivational. Our real problem here is with S and T matrices. And we have two separate models, one for a T matrix that has a predefined dimension for the model, and another that is an error matrix that comes from an ionized XX chain model. In this case, the dimension of our braid circuit, of our quantum circuit, is going to grow as to the power of n, because when we want to increase the number of strands of our circuits, we perform tensor products. And so it becomes a very intensive process to calculate this. To handle this, we use randomization techniques to be able to rescale our circuits to circuits with a fewer number of inputs and outputs. Or we can shift the eta metric, choose a new syntax, as is my proposal. So the no-cloning theorem, as I told you, it looks like this. These equations 4, 5, 6 with this eta metric. If it was identity, it would be the no-cloning theorem for Euclidean metric. But in this case, this is for general pseudo-Unitary group. These authors propose this as they proposed an algorithm that should manipulate modules of a optical circuit to emulate a pseudo-Unitary group, and thus, according to them, they achieved a circuit capable of quantum cloning of non-orthogonal states. Why? Because they didn't use the Euclidean metric. And pseudo-Unitary groups defined based on these constraints. If eta equals identity, again, we have the Unitary group. And the other section where the where the pseudo-Unitary groups appear so much is in S matrix and T matrix theories. We have several conventions for S matrices and T matrices based on the initial and final states, but we have generally the same diagram. So we can build our S matrix. This P matrix is a permutation matrix. We can build the mappings, for example, C and D are the incoming states, and AB are the outgoing states. You can map C to A, you can map C to B, etc. And we have several permutations that represent other S matrices, other T matrices. And we need to account for that when we're comparing models of T matrices and S matrices and A matrices. So when we map a S matrix to a T matrix, we perform an operation in an equation system. This operation, I call it, here I labeled Y with the index ik, because when you solve this equation system by permuting the vector entries from one side to another side, we perform simultaneously a partial inversion in this matrix. This is just these two systems are equivalent. This is just an application of solving the equation system for a new set of vector entries as input and output. This wasn't recognized as a group. This wasn't recalled as a group in literature very often. Actually, I never found someone saying this is a group, but this is a group, and by applying this along a whole diagonal, we invert the matrix. So I call it partial inversion. This partial inversion, when I apply this in a matrix Z, we have this equation, and it has a matrix representation with identity plus a commutation operator plus a custom commutation operator that I called this star commutator, and it looks very much like the Young-Baxter equation that occurs in Braid theory and statistical mechanics, like this. And some properties of this group, of course, it's associative, it's idempotent, and it's commutative along a diagonal. we perform inversion on one object, the matrix, and we performing permutation of vector entries at the same time. So it has some properties of this algorithm, the entry-wise version with some orders that we find is in pi and NumPy. We find that the entry-wise version of partial inversion is 2 orders of magnitude at least faster than SymPy's LDL, for example. But it's still not faster than NumPy's. Okay, what else does Y do? We already know how to invert matrices. So what can we make of this new group? Not so new, but what can we make of it? Total inversion commutes with similarity transformations. We already know that. When we apply this partial inversion in case of an S matrix as a general representation of an unitary group, we're mapping it to a pseudo-unitary group. So the constraint, the pseudo-unitary constraint changes, and here appears the sigma 3 on the pseudo-unitary group constraint. In the case of the A matrix, when we apply a partial inversion to obtain it, we have this other constraint. And we can try to find a general solution. What is the final metric that are going to obtain for this new pseudo-unitary group as due to the application of this partial inversion and this initial metric eta, but is a bit too laborious, the solution. And interesting metric changes will occur if you have constraints like the unitary group or an orthogonal group, another group. If you take only a general matrix, you'll be mapping just to the total inversion of the matrix. So we're interested in some constraints that involve orthogonal transpositions and orthogonal inversions. They are representations of the dihedral group, and they obey this algebra with these generators for transpositions, these ones for inversions along the diagonals. This Y1 is applying partial inversion along the main diagonal. This gives the total inverse. Y2 along the secondary diagonal, and Y3 is the composition of both that gives this operation of these sigma matrices. That in this case, of course, sigma matrix is a matrix once along the secondary diagonal and zeros elsewhere. We represent these transpositions as similarity transformations in this case. And we also have the polygroup generators, and we represent them like these operators as similarity transformations, because when we apply successively partial inversion, in this example for this cycle from the main diagonal of the matrix going clockwise, we see that we have orders in their groups. They are well mapped, but we have here sigma 3 instead of identity. We have I sigma 0, sigma 0's identity. I sigma 0 tau 2. This tau 2 is this guy here is representing a similarity transformation rather than a single matrix for the metric. Then we come back to identity, and we have all the metrics appearing here, all the similarity transformations for our constraint. And these operations, you see that they are changing within a discrete group, a closed group. This group is formed by representations of the dihedral group for partial inversion along axis, transpositions, conjugate transpositions, and generators of rotation. They all have one generator in common, that is this tau 3, this transposition along an axis that passes through the matrix. So yeah, for the 3 of these groups, we have a system of 3 orthogonal axes, and we imagine them passing the matrix through the main diagonal, the secondary diagonal, and the section where they cross. Okay, we have this Y walks the metric of the pseudo-unitary group within a graph of group generators. by conveniently considering transpositions and inversions as actions of metrics. But how can I use in my circuits? Can we choose? Can we walk at such as to choose a group with a more convenient composition rule? That's the case that I want to study. That I am studying, and I'm going to show you something about it. We used in this 2D toy model, this is with orthogonal S matrix that gives this T matrix, this A matrix, and the T matrix has this composition rule. So when we apply products of T matrices, we obtain the resulting T matrix within the same group. We want something similar for the A matrix, so that we can obtain a T matrix by applying partial inversion. And thus, we can grow our diagram with T matrices along this direction and with A matrices along this direction. By solving a system of stacked subsystems, stacked equations of stacked matches along the diagonal for our larger system, we find this A of n minus 1 as the A matrix, such that if you multiply these A matrices, we can apply partial inversion and obtain the respective T matrix. Okay, that's a good point. Now that is the real problem, that y, this operator y involves 1 over zik, so we can have infinities, and we need to be able to get out of these infinities. We can apply partial inversion along the diagonal and have a total inverse of a matrix, even if it has zeros, by considering the zeros as symbols. And here we obtain a real matrix when we substitute these symbols by zeros again. So that is this possibility. And when we take another matrix that is a form of harmonized model, we have this problem that when we apply the partial inversion to get the A matrix representation, here we understand this R matrix as a transfer matrix. So we can try to find the S matrix and the A matrix for this matrix. We find lots of infinities, and we need a custom simplification function to treat this. And this is a problem that may appear when we try to draw a diagram. So I couldn't go any further from this. Finally, we know that there is a group, partial inversion group, that maps S matrix to T matrix. And the metric walks within a discrete group. We obtain the A matrix for a two-dimensional toy model, and if this symmetric group was made continuous, this would imply that that is a continuous algorithm for matrix inversion, and consequently there are infinitely many metrics in infinitely many pseudo-unitary groups to try the Knopf theorem. Thank you very much. That's all. We're open for questions.
Thank you very much, Dennis. It's been a great presentation. Thanks a lot for it. I think that we should start the next talk immediately. So thanks again, and
yes.
Much.
Yes.
Okay. Now, Dr. Hamid Tebyanian, hopefully I have correctly pronounced your surname.
Yes.
Will be delivering a talk. Meanwhile, as he tries his slides, let me say that he holds a postdoctoral fellowship at the University of York in the United Kingdom, and his talk is entitled Randomness Generation from Quantum States Indistinguishability with Untrusted Devices. Thank you very much, Hamid, for being with us, and we'll wait for you to have your presentation ready.
Thank you. Can you see my screen or?
Not yet.
What about now? Can you see it?
Yes, now we can. Yeah.
So this is Hamid Tebyanian from the University of York. Before getting to the presentation, I would like to thank the organizer for organizing this event. So in this presentation, I'll talk about randomness generation from quantum state indistinguishability with untrusted device. Let's start with randomness definition. A string of numbers called random if it's uniformly distributed, unpredictable, and also trusted. Obviously, this process is not random because this guy is untrusted. So lack of pattern or any order is really important for any quantum random number generator, or any generator, not even quantum. And no pre-established theory or pattern or strategy should be able to predict the random event. But why randomness is so important for us? Randomness, random numbers has many applications in science and technology, for instance, in simulation, like Monte Carlo simulation, in gambling, like casino games, where unbiased random number generator is really important, and more importantly, in cryptography. Consider there are two parties want to communicate through a public channel, let's say satellite, and let's call these two parties Alice and Bob. So Alice wants to send a message, which is, say, wrong. So her messenger converts the message to a binary sequence of 0 and 1s. And if she sends it to the public channel, since it's a public channel, everybody has access to it, and a third party or eavesdropper can intercept the message, read it, and possibly change it. Easy solution to this problem is combining the original message with the random key with the same length of the original message. And then she can encrypt the message and send the encrypted message to this public channel. And the communication will be secure as long as the random key is private. On the other hand, the other party, which is Bob, received the message. And by subtracting the random key from the encrypted message, he can have the original message. Distributing random key between two parties is another topic which is out of scope of this talk, but you can search for quantum key distribution, which is a quantum way of distributing the key. So with this example, I show the importance of privacy of random number generators and random numbers in data encryption. Now the question is how we can generate random numbers. There are mainly two types of generators, classical and quantum. In the classical generators, the generation of random numbers is based on deterministic phenomena. There are mainly two well-known classical generators, like pseudo-random number generator and hardware random number generator. In the first one, which is pseudo-random number generator, the generation of random numbers is based on an algorithm on a computer or a pattern. So if you know the algorithm, then you can predict the outcome, so it's not secure. Then we have hardware random number generator, which is based on classical physics phenomena, for instance, tossing a coin. But consider if you know the initial power, then classical physics provides you the evolution motion, and then you can predict the outcome. So regardless of how complicated is this phenomena, because it's deterministic, so it's predictable, so it's not secure. On the other hand, we have quantum generators, which the generation of random numbers is based on intrinsic random behavior of quantum mechanics, which is purely random. Therefore, it's unpredictable, so it's secure. But even though quantum mechanics can assure the randomness theoretically, but what if the experimental devices is somehow made or controlled by a third party, or in worst case, eavesdropper? In that case, the security can be compromised. Let me illustrate this better by this example. So consider a quantum random number generator, which made of a single photon source, a polarizing beam splitter, and two single photon detector. So from this single photon source emits polarized single photons to the polarizing beam splitter, and depending on the polarization of the single photon incident on the polarization beam splitter, it either gets reflected or transmitted. And based on the click we get from the detector, either 0 or 1 can be assigned, and random numbers can be generated. Consider the case that the source is controlled by eavesdropper, so she can prepare entangled state, keep one pair and send the other one to the polarizing beam splitter. The user do the process, and it seems to be random because it follows the quantum mechanics, but eavesdropper knows everything because she holds the another pair of entangled state. So it's not secure at all. Other case could be classical imperfection of the devices. For instance, consider the dark count of the detector. So dark count of the detector can cause a click without any single photon coming to the detector, and like you will have many click due to other source than quantum mechanics. So it's really important to exclude all the classical all the numbers caused by the classical source from the quantum one. In this slide, I would like to talk about a project called AQRAND, which is a project defined in the UK. AQRAND stands for Assurance of Quantum Random Number Generators, and it tries to analyze and study different quantum random number generators and try to define different source of side information, whether classical or quantum, and exclude all these classical ones and just have the quantum source, which is quite private and genuine, and it's trustable. So there are industrial and academic partners, including University of York and NPL, which theoretically and experimentally try to somehow certify pure and quantum randomness from these industrial partners. To give a better explanation, consider this example, which we have a single photon source, then there is a balanced beam splitter followed by 2 single photon detectors. Again, depending on the beam splitter, so the single photon either get reflected or transmitted, and random numbers can be generated. But consider if the beam splitter is not completely balanced, so there is some classical imperfection. So it's like, instead of being 50-50, it's like 40 to, I don't know, 49 or something, or the problem of a single photon detector like dark cones, like after pulsing effect, and etc. So in this, simply in this project, we try to understand the trusted and untrusted part, and we also try to consider classical and quantum side information. For instance, in this simple example, we have the classical side information or quantum side information of a single photon source, beam splitter, the detectors, and also environment. For instance, the whole environment can be quantumly or classically correlated with this device. So we can estimate the final extractable amount of randomness by using conditional mean entropy, which this entropy or mean entropy is conditioned on classical or quantum side information. For more information about this project, you can visit the website, which is aqrand.org. Okay, back to quantum random number generators. QRNGs in general can be divided into 3 categories: trusted device, semi-device independent, and device independent. So in the trusted device, the user needs to trust on the performance of the devices, and almost all of the commercial QRNGs are based on trusted device because it's affordable, easy to implement, the generation rate is high, but the security can be compromised, as I give you example in a few slides, in previous slides. On the other hand, we have device independent, which they provide the highest level of security, but at the same time they're so complicated and the generation rate is low. They are usually based on like a violation of Bell type inequality, and so like they are far from being practical. So like it's not the best option for commercial purposes. In the middle, we have semi-device independent, which can offer a great trade-off between security and ease of implementation and the generation rate. So in this presentation, I present a semi-device independent quantum random number generator based on prepare and measure scenario, which we have an input to the preparation part, and the outcome comes out from the measurement part, and based on input-output correlation, we can certify some randomness. So the measurement is completely untrusted, so we see it as a black box, but there is a single assumption on the preparation part, which you can see here in the black box, like we have a beam splitter, power meter, and variable optical attenuator, which we suppose it is trusted, and the rest of preparation device is untrusted. Before explaining about the trusted part, let me give example which illustrate this setup. So consider we have 2 coherent states represented by these 2 balls here. When they're well separated, it's easy to distinguish them, but when they share some overlap, they become indistinguishable. Consider measuring a set of coherent states when they share high overlap and getting click here in the intersection area. It is impossible to understand what is the source of this click. This ambiguity in measuring non-orthogonal quantum state is the randomness source of this protocol. Then back to the experiment. So in this trusted part, we can check the energy, and theoretically we show that if the energy of the state is below some threshold, then we are sure that state shares non-zero overlap. So when they have non-zero overlap, we are sure that there's some randomness. So with this power meter, we can monitor the power, and if it's not in the allowed area, so we can apply some attenuation to the signal going to the measurement part. So the security is a general. So the security summation is a generalized one for n input and the outcome. So multiple input and outcome. Here I just explained a CV case, but also it can be implemented in DV by using, like, for instance, time-bin encoding scheme. But here I just explained explain it in CV domain. So you can use the phase shift keying scheme to encode the information. For instance, for two input, you have binary phase shift keying. For three, we have ternary phase shift keying, and so on and so forth. And for the measurement, we can either use homodyne or heterodyne detection. Homodyne gives information about one field quadrature, let's say x, while heterodyne detection gives information about both field quadrature, say p and x. By increasing the phase space into more subspaces, you can increase the number of outcome, like so from, say, minimum of 2 to n. And in this work, we show that by increasing the number of outcome, we can extract more entropy without need of changing the experimental setting. Yeah, well, because heterodyne detection gives information about both field quadrature, so you have access to a two-dimensional outcome. So there are many ways to configure the outcome. So you can just also check the different configurations. So here we can see the result. So this figure shows condition entropy as a function of the number of outputs for like only for TPSK and QPSK modulation scheme using heterodyne detection. So going from 3 outcome to 4 outcome, I showed the amount of extractable entropy, or randomness, say, goes from 0.22 to 0.27 without we don't need to change the experimental cell. For instance, you can consider you have a device which generates some here quantum random generator. You don't need to touch it. Only by changing the post processing, simply by increasing the number of outcome, you can increase the amount of extractable random numbers. So you can increase the rate, which is a good achievement. And here is the conclusion. In this presentation, I present a novel semi-device independent QRNG with few reasonable assumptions. This is really easy to implement with commercially off-the-shelf components, and it is really high. So it's a high performance. You can compare it with like commercial generators, and the security is like generalized, can be implemented for multiple input and outcome. And I would like to thank for your attention. And I'm happy to take any question either now or you can send me by email.
Thank you very much indeed for your talk. It's a pleasure to learn what you've been doing over there in York. And I don't see any questions, neither on the chat nor on the question and answers. So maybe what we could do is we just, well, again, to thank you. And then let's have a break so that the next lecture to be delivered by Marcin Jastrzebski, hopefully I have pronounced it correctly. If not, tell me so, Marcin. Begins in 5 minutes' time. Okay? Thank you very much.
Thank you.
So stay, don't log out. Stay here and we just start in 5 minutes' time. Okay, well, let us welcome Marcin Jastrzebski from the University of Warsaw in Poland, who will deliver, he holds a PhD studentship there, and he'll talk about using ultra-resolution spectrometry to measure femtosecond impulses. Thank you very much, Marcin, for being with us. Go ahead.
Hello, thank you for the introduction. So let me now try to share my screen. Okay. Can you see it? Can you see my presentation?
Yes, we can.
Okay. So here is the, oh, sorry, let me maybe take this here. Okay. So here is the title of my talk, as it was already said. My name is Marcin Jastrzebski, and I want to show you the work that we've been doing in Center for Quantum Optical Technologies in Warsaw, in Poland. But I actually, oh, I can't, oh, now I can. I actually wanted to start with this picture because maybe some of you already see what this is, and this is actually a laser that I've been working with, and probably all of you have seen a laser in your life, but this one is a little bit special. So it doesn't have an intensity that is constant in time, but instead it generates very fast pulses of light, and it's called a femtosecond laser, since those pulses last femtoseconds, which is 10 to the minus 15th, and such pulses can be very useful in medicine or biology or chemistry. And here we made we had an idea how to measure those pulses, because there are some methods, but they have their flaws, all of them. So let me now tell you something about those femtosecond impulses. So as I said, they are very short in time, so we know exactly when the photons will arrive. And since they have to obey the uncertainty principle, we can't know very precisely the time and their energy. So the wavelength of such a laser is not, we can't tell it really precisely. So here you can see that the intensity in time, it has, this is the impulse. But if we want to know the spectrum of this laser, it's very broad. And in our case, it's 12 nanometers, which is really broad. The whole laser is, we say, 800 nanometers, so it's near infrared. It's you actually can't see that, but when the power is very very big, maybe you can on some elements. So let me tell you quickly about the whole idea in this experiment. So we have our femtosecond pulse, and we use a beam splitter to split it into two separate copies. And we have one arm, and we shift one of the pulses here in time relative to the other. And in the other arm, we shift the pulse in frequency a little bit. As you can see, it's blue, so it has a different wavelength. And then we measure the interference of those impulses. So to show you what's going on here, so let's say we have two identical pulses, and as you can see, they overlap perfectly because they are not different from each other in any way. And when we shift one of them in time a little bit, you can see that they overlap less. And then we shift in frequency, and they also they may stop overlapping or overlap just a little bit. So that's the idea. And here I wanted to tell you how we generate those shifts both in time and in frequency. So here is our how we make the time shifts. So this is a stepper motor here that we control from the computer. and here is the collimator. The light travels here and gets into this fiber. So by changing the position of this collimator, we change the distance that the light has to travel. And the frequency shifts are a little bit less trivial, because this stepper motor and the moving collimator is, pretty trivial time shifts. You just change the length of the path that light travels. So to achieve frequency shifts, we use an electro-optical phase modulator. That's this box here in the lab. And here you can see this is the input, so it's a fiber, and the light comes in here. And there is output, so the light comes out here also with a fiber. And there you can see the RF symbol and its radio frequency. And for us, it's 15 gigahertz. So we essentially have a photodiode to have a clock, because we have to synchronize this RF signal with those pulses, and then we generate this RF signal. And inside this box there is a crystal. It's called lithium niobate, and it has an interesting property that when we apply voltage to this crystal, its refractive index changes, and by applying linear voltage here, we can achieve linear phase shifts and therefore shifts in frequency. So now you can say, okay, you have the setup with time shifts and frequency shifts. You have some kind of modulator that enables you to shift. What's next? And the thing is, we have to know how much shift do we have, because as I said before, the spectrum of this laser is very broad. It's 12 nanometers. And if you want to measure the interference while shifting in frequency, we would like to have at least as much shift as the spectral width of the impulse. So the question is, can we shift by 12 nanometers? And the answer is no. We can shift only by 0.2 nanometers. And this shift depends on the power of this radio frequency signal and on its frequency. And we, did everything to make this shift as huge as possible. But that's kind of the limit. We can't just burn our device. So we have to do something with the spectrum. And as you may know, there are elements called spectral filters. You just insert them into the beam, and you get a narrower spectrum. But we didn't actually have such narrow filters, and also we wanted to be able to change it for different measurements. So here comes the first setup, which is actually, we can say it's a spectrometer. It's a 4F spectral filter. And here is the scheme of this setup. So the whole idea is just that we use a diffraction grating, and as you probably know, diffraction grating works so that it reflects different wavelengths at different angles. So we basically split the beam into some spectral components, and then we use a slit, very precise slit that we can regulate to cut some of those wavelengths, and therefore make this beam have narrower spectrum. And it's called 4F setup because as you can see, there is the lens, and the distance from the grating to the lens is equal to the focal length of this lens. Again, here to the slit is the F, and here also, and here. So that's why it's called the 4F. And the second grating is basically to combine this beam, like all those wavelengths together again, and then the light travels. As you may see, actually using we are not using the first order diffraction because you can have many orders of this diffraction when you use a grating. The first order of the diffraction would go somewhere like here, but we had to use the second order so that the resolution is better and we can narrow the spectrum as much as we want to. And now you may say, okay, you have this filter, those shifts in time and frequency, but how can you measure those shifts? So the answer is we needed a spectrometer. So how spectrometer works, you just have a grating and some kind of detector, and you measure the position of the beam, and you can attribute it to some wavelengths. But the commercial devices are not precise enough. As I said, we have frequency shifts around, or wavelength shifts, I should say, 0.2 nanometers. So the spectrometers that you can buy online have like 100 nanometers range, and it's just not precise enough. So we had to build our own spectrometer, and here is how it looks. So again, there is a grating, as I said. We use the second order diffraction and then reflect it back on the grating and use the second diffraction of the second diffraction, which gives us effectively the fourth order of the diffraction. And the higher the order is, the better the resolution is. And using this spectrometer, we were able to measure all those shifts to be able to narrow the spectrum. And it's, you know, you may say it's a simple device, but it was really crucial for the whole experiment. So you may ask, okay, you have the spectrometers, you have the shifts, modulator, etc. What do you measure here? So the quantity that we measure is called, it's the absolute square of the absolute value of a quantity called short time Fourier transform. And it's basically, you know, an integral of those epsilons are electric, the amplitudes of electric field. As you can see, one of them is shifted in time, and the shift is the tau, and the other is shifted here in frequency, mu. And we calculate this short time Fourier transform with respect to tau and mu. And then what we do is we make a two-dimensional map of this quantity with respect to those mu and tau to get some pictures. So let me show you those pictures. Here at the you have the experimental data here for certain spectral widths. It's full width at half maximum. We have some strange units here, but grad per second means gigahertz times 2 pi, because we use the angular frequency. And at the bottom, we have the simulation, the computer simulation that we wanted to compare those experimental data with. As you can see from this map, you can see how much you have to shift the pulse in frequency so that they stop interfering and therefore know their spectral width. We may also detect the chirp of the pulse. The chirp looks like a little bit like this pulse was a little bit inclined. So that would be the chirp. And the interesting thing is here that we can see these like 4 legs, or it looks more like a star for me at least. So you can also see it in simulation, and it turns out that we are able to cut our impulse with this in this 4F setup so precisely that it's more of a resembles more of a square or rectangle rather than Gaussian distribution. And when we apply in the simulation that the spectrum is a rectangle, not a Gaussian distribution, we actually get those artifacts, let's say. Because if that was just a had a Gaussian spectrum, we would have more of a ellipse. So, this maybe look weird, but it's coherent with the simulation. So to quickly summarize, it is a new method for measuring light pulses. We control the shifts electronically, and as detectors, we use single photon detectors or just photodiodes. And the most important thing is there is single photon level sensitivity, because as you probably saw, there are no nonlinear effects here. So, and they tend to be very inefficient energetically. So you need a lot of power to pump some crystals, to generate second harmonic or something like that. We don't have anything like that here, so we don't need any nonlinear effects. Thank you very much. That's all I have to say.
Thank you very much indeed, Marcin, for your great talk. Now let's switch. Well, we'll see you around. Thank you very much. Let's stay in touch.
Thank you.
And now let's finish our session with a great talk by Dr. Alejandra López Vázquez from the Universidad Autónoma de San Luis Potosí. She holds a postdoctoral fellowship in that university, and the title of her talk is Laser Systems for Complete Manipulation for Atomic Gravimetry Using a Single Laser. Alejandra, thank you very much for being with us. I'll pass it on to you.
Thank you so much. Hi. I will speak in Spanish.
Sorry, yeah, I forgot to say that. Well, as you may wish, but it's up to you. But it was originally stated that your talk would be in Spanish. So if you are keen on doing that, let's go ahead.
Okay, thank you.
Okay, so será en español. Muchas gracias.
Ok, bueno, ¿pueden ver mi presentación? ¿Sí? Sin problema.
Y adelante, se ve muy bien. Muchas gracias.
Ok, bueno, mi nombre es Alejandra López Vázquez y les voy a presentar pues mi trabajo, el cual se trata sobre un sistema láser para realizar experimentos de gravimetría. La particularidad de este sistema es que solo trabaja con un solo láser. Bueno, entonces, como introducción, les quiero hablar un poquito sobre lo que hacemos en el grupo de trabajo al que pertenezco, en el cual hacemos gravimetría mediante interferometría atómica, donde somos capaces de dividir la función de onda de un átomo mediante pulsos de luz para obtener información acerca de la aceleración de gravedad. Y bueno, ¿por qué nos interesa medir la aceleración de la gravedad? Bueno, el dinero, aparte de otras cosas, y porque, como observamos o podemos observar en la figura 2, vemos que al realizar una medición de la aceleración gravitacional, podemos tener cierta información acerca de alguna propiedad del planeta. Entonces, si nosotros estuviéramos interesados en la extracción de agua o de gas, por ejemplo, nuestro aparato debería de ser capaz de medir hasta el sexto dígito, que sería este de aquí, el cual nos da información acerca sobre información sobre los reservorios que hay en el planeta. Muy bien, entonces el sistema láser que les voy a presentar es capaz de realizar estos experimentos con la particularidad de que es un sistema portátil y que puede ser llevado a diferentes localizaciones para hacer estas mediciones. Muy bien, entonces voy a hablar un poquito sobre que este sistema láser pertenece a una colaboración que lleva el nombre de Gravico. Y esta colaboración reúne a 5 universidades mexicanas para realizar un gravímetro portátil. Entonces, estas universidades están a cargo de la realización del único láser que se ocupa en los experimentos. Estas 2 universidades, y en particular yo, estuve encargada de realizar el sistema láser, el cual tiene como entrada el láser inicial y a la salida puede dividir este haz en múltiples frecuencias para poderlo mandar a la cámara de vacío y tener la interacción con los átomos. Este último módulo o la cámara de vacío estuvo a cargo de estas dos instituciones. Y bueno, si les interesa saber un poco más acerca de nuestro grupo, esta es la página de internet. Muy bien, entonces pasemos a hablar en específico de este sistema láser, cuya principal característica fue, o más bien nos concentramos en que todo lo que vemos o todo lo que tenemos en un experimento o en un laboratorio, convencional, donde se llevan a cabo estos experimentos de gravimetría, pudiéramos compactarlo lo más posible, lo cual logramos. Y bueno, en la figura 4 les enseño un diagrama de cómo fue que quedó nuestro sistema láser. Entonces, si ven, el principal objetivo o meta fue que todos estos cientos de componentes ópticas y electrónicas que tenemos las pudiéramos meter en este pequeño rack. Entonces, nuestro sistema láser está compuesto principalmente, o más bien está compuesto de dos módulos. Un módulo que lleva toda la óptica del experimento y un módulo que lleva toda la parte de microondas y electrónica del experimento. Entonces, voy a hablar un poquito sobre el corazón del módulo óptico, porque yo siento que esta es la parte más importante y la parte más bonita de nuestro sistema láser, en el cual, como ya he mencionado, recibe un único láser o haz láser, el cual pasa después por un único modulador electroóptico, que es este de aquí, el cual nos da múltiples frecuencias en el rango de los gigahertz y después pasa por un único amplificador que nos da la potencia necesaria para los experimentos y por último pasa por un modulador acústico, el cual nos permite dividir espacialmente cada una de las frecuencias que nos generó el modulador electroóptico. Y bueno, ustedes se preguntarán si estos sistemas ya existen en el mundo. Y pues la respuesta es sí, sí ya existen este tipo de dispositivos en el mundo, pero la diferencia con nuestro dispositivo es que solo necesita una de estas componentes. Entonces, por ejemplo, aquí yo hice mi comparación con dos módulos de otros grupos, los cuales pues inicialmente están ocupando 4 láseres o 2 láseres, ocupan varios moduladores acústico-ópticos, varios amplificadores e inclusive su sistema no es un haz, más bien su haz inicial o su láser inicial no es un láser de 780 nanómetros inicialmente. Es un láser de 1560 nanómetros, el cual después tienen que doblar para obtener 780 y eso les añade componentes extra que nuestro sistema no tiene. Entonces, pues quiero hacer énfasis en que nuestro sistema quedó mucho más compacto y utiliza las componentes mínimas necesarias para realizar estos experimentos. Pero, bueno, se preguntarán, bueno, ¿por qué ellos no lo hicieron o por qué no se atrevieron a hacer esta parte de solo ocupar una componente de cada tipo? Bueno, pues digamos que el dispositivo esencial de nuestro sistema es el modulador electroóptico. Cuando nosotros le mandamos una frecuencia a este modulador, nos genera diferentes múltiplos de esa frecuencia y eso hace que podamos tener nosotros problemas con nuestro experimento. En particular, nosotros hay partes de la secuencia del experimento donde necesitábamos 3 frecuencias, entonces mandamos 3 frecuencias al mismo tiempo al modulador electroóptico y pues me genera varias frecuencias extras no deseadas a las cuales les llamamos no linealidades y estas podrían hacer que nuestro experimento no se llevara a cabo. Sin embargo, nosotros hicimos un análisis de la potencia que debería de tener cada una de estas, digamos, potencias iniciales y que sus no linealidades nos provocaran dispersión de fotones en comparación con las frecuencias deseadas, ¿no? Entonces, por ejemplo, aquí en la gráfica podemos observar, estas son la dispersión de fotones de las frecuencias que deseamos, y las demás, y la dispersión de fotones de las no linealidades están bastante suprimidas, y como referencia, pues son más pequeñas que la portadora misma, que está alejada más de 2 GHz de nuestra frecuencia de interés. ¿Ok? Y bueno, esto pues fue la parte del rack de óptica, y la parte del rack de microondas. Pues aquí muestro un diagrama en la figura 8, la cual podemos ver que está constituido principalmente de sintetizadores de microondas y de radiofrecuencia que utilizamos para mandar tanto al modulador acústico como al modulador electro-óptico. También una particularidad que tiene este sistema es que tiene su sistema de control, el cual nos permite mandar la frecuencia por el camino correcto y en el tiempo que lo necesitamos. Y en la figura 9 les muestro cómo quedó finalmente nuestro rack, o cómo está montado nuestro rack. Este es un rack de 9 pulgadas. Y bueno, eso prácticamente son nuestro sistema láser compuesto por estos dos racks. Y bueno, como conclusiones, pues quiero resaltar que pudimos tener nuestro sistema láser bastante compacto, y en comparación con otros, utiliza la menor cantidad de dispositivos, que son uno de cada tipo. Y aparte, hemos podido demostrar que tenemos una trampa atómica, realizamos molaza, e inclusive nuestro sistema hace una fuente atómica. ¿Ok? Entonces, hace lo mismo que los otros sistemas, e inclusive un poquito más. Y solo como un comentario adicional en esta parte de las conclusiones, ya que nuestro sistema puede realizar manipulación atómica con luz, podría implementarse también para las aulas en enseñanza, ya que su precio promete ser bastante accesible. Y bueno, esto es todo por mi parte. No sé si tengan algunas preguntas.
Espérame un momento, por favor. Ahora sí ya. Muchísimas gracias, Alejandra. Qué trabajo tan interesante. Te agradecemos de todo corazón que hayas compartido con la audiencia de Quantum-Latino, con todos nosotros, los avances que han tenido en tu trabajo, en tu grupo de investigación. Y no veo preguntas. Demos un minuto para ver si alguien quiere hacer alguna pregunta.
Claro.
Y si no fuese así, pues con tu conferencia de forma magistral termina la sesión de hoy. De nuevo, muchísimas gracias por tu tiempo, por el tiempo que requiere preparar presentaciones de este estilo, que todos los que pasamos por un doctorado, por un postdoc, sabemos muy bien lo que esto implica. Así es que muy agradecido. Y pues bueno, yo creo que deberíamos de despedir la sesión por ahora. Nos vemos mañana a las... por favor. Nos vemos mañana a partir de las 8 de la mañana. El día de mañana, el 9 de junio, es de muy interesante para en cuanto al latino de los temas que vamos a tocar, porque vamos a hablar de industria, el cómputo cuántico, las tecnologías cuánticas, por ejemplo, que nos acaba de presentar Alejandra, pues son temas que a todo académico nos hace llorar, así, lágrimas de alegría, ¿no? De este tipo, vas a ver que podemos dedicar nuestras vidas a este tipo de actividades, y también a efecto de que nuestras sociedades tengan los beneficios económicos de creación de riqueza material, desarrollo de nuevos productos, desarrollo de empleos, razones para ir a la universidad, ¿no? Razones para estudiar doctorados y dedicar nuestras vidas al trabajo productivo en el que ser científico. Bueno, pues esas llegan cuando se construyen los puentes entre la academia y la industria. Mañana entonces estaremos hablando de este tema, de industria y gobierno. Tendremos, entre otros conferencistas de talla internacional, la participación de Débora Bereviches, quien es mundialmente famosa en el tema de la tecnología cuántica, quien ahora trabaja en Finlandia, estudió el doctorado en Stanford, muy conocida por diversas razones, en particular por empujar de manera constructiva y sistemática la agenda de la participación de mujeres en STEM, en ciencia, tecnología e innovación. También estará con nosotros Emilio Hughes Salas, quien es, bueno, él hizo el doctorado en Inglaterra. Yo tengo el gusto de conocerlo desde hace bastante tiempo, que estudiamos en la misma universidad de la carrera, y después se fue a Bristol varios años a hacer investigación, y ahora trabaja para British Telecom en el Reino Unido. También estará con nosotros como conferencista magistral Alberto Treviño. Alberto Treviño es el director general del Centro Global de Innovación de AstraZeneca en Guadalajara, Jalisco, y hay un trabajo muy interesante que se desarrolla, como seguramente ustedes ya saben, y si no mañana se van a enterar plenamente. Una de las líneas más interesantes de aplicación industrial del cómputo cuántico está en la industria farmacéutica, básicamente por la solución de problemas de optimización y por el hecho de que la simulación de construcción de nuevas moléculas en supercomputadoras y su aplicación en fármacos puede tomar meses o inclusive un año, ¿no? Un año y tantito más de simulación en supercomputadoras. Entonces mañana vamos a escuchar la visión del centro que dirige el ingeniero Treviño respecto de cómo utilizar cómputo cuántico en la industria de farma, y en ese tenor van a estar todas las conferencias. Así es que muchas gracias, que tengan muy buenas tardes, buenas noches para todos, y nos vemos el día de mañana. Hasta luego.